Welcome back to the deep dive, where we tear through the research and all the notes you send us to pull out the ultimate, most surprising nuggets of knowledge.
We're not here for the basics.
No, not at all. We're here for the revelations, the facts that make you rethink everything you thought you knew about the universe and, your place in it.
Absolutely.
And since we're talking about these counterintuitive truths, let's start with a piece of trivia that just always messes with my head.
Okay.
And it's the perfect launch pad for today's cosmic journey. What do you think a common cumulus cloud weighs?
Ah, that's a great one.
You see them floating up there? They look like cotton balls. Maybe a few tons. 10.
Most people guess way, way low on that. I mean, they're held up by air, right? So how heavy can they be?
Right.
But if you actually calculate the volume of water droplets inside that white, fluffy appearance, you find that a standard cumulus cloud, the kind you see on a summer day, contains roughly 1 million tons of water.
1 million tons. That is insane.
It is 1 million tons, yet it floats. It's just completely defying what our intuition tells us about mass and gravity.
So how does it do that?
Well, the reason, as your sources detail, is pure physics. Its density is just slightly, we're talking about maybe 0.4% lower than the surrounding warmer air.
An amazing, profound, and just utterly counterintuitive truth about our own atmosphere.
Exactly.
And that, my friends, is our mission today. You provided this fantastic stack of materials on the cosmos, on human adaptation to extreme environments, and the sheer weirdness of life beyond gravity.
A really fascinating collection of research.
And our goal is to find the hidden density, the million-ton secrets within all that information. We're going to examine the quirks of human perception in the void, the strange smell of dying stars, and the surprising cosmic truth about the origins of your own body mass.
So we're moving from, paradoxes in our own atmosphere right down to the molecular level. We're asking why space smells like barbecue and what ancient stellar dust has to do with your DNA.
Okay, let's unpack this. Our first big paradox. It involves our most primal sense. Smell. Specifically, the olfactory paradox of a vacuum.
Yeah, this is a great place to start.
I think so too, because logically, space shouldn't smell like anything, right? Smell needs molecules, volatile molecules, to hit our olfactory receptors. Space is, well, it's the ultimate vacuum. It's empty.
Precisely. If you were exposed directly to the vacuum of deep space, you certainly wouldn't be smelling anything. For obvious reasons, your body would be in a catastrophic crisis.
Right.
The smell itself is a secondary phenomenon. It's an indirect thing. It's a chemical reaction that only happens when astronauts bring material from the vacuum back into a controlled, pressurized, oxygen-rich environment.
So into the airlock of a spacecraft, or even just inside their helmet after they've sealed it in.
Yeah, that's the only place it can happen.
But the reality, and this is confirmed by decades of reports, is that astronauts consistently report a strong, distinct, and apparently highly memorable odor.
Oh yeah, they all talk about it.
It clings to their suits, their tools, the very airlock after a spacewalk. It's not some subtle scent. It's like the signature scent of the final frontier, captured and brought inside.
And the consistency in the descriptions, I mean, you have astronauts from different countries, different agencies, different missions. That's the strongest scientific clue that something real and reproducible is happening chemically.
Even if the words they use to describe it are, all over the map.
That's putting it mildly. The descriptive language is wildly inconsistent.
Inconsistent is an understatement. It's like a cosmic tasting menu, and it's all tied to combustion.
Right, that's the one theme.
Former astronaut Greg Chamadoff, he described it simply as a really, really strong metallic smell. But then you get Don Pettit, and he adds this layer of nuance. He called it a pleasant, sweet, metallic sensation.
A pleasant, sweet metallic.
And then he immediately likened it to sweet-smelling welding fumes.
That's a bizarre sensory fusion right there. Sweet, metallic, and burnt. You don't usually put those together.
No, you don't.
And that combination, that metallic and high heat processing, that is a constant refrain. Then we get into the food references, which are even stranger.
Yeah, the seared steak camp. Chris Hadfield called it burnt steak.
And UK astronaut Tim Peake, he said it was like a British summer barbecue, burning sausages on a charcoal grill. Very specific.
Barbecue, metallic, welding fumes, burnt steak, ozone, gunpowder. It's a really consistent theme of high heat, friction, combustion.
It just screams rapid oxidation event, chemically speaking.
Exactly. And then you have the truly baffling outliers, which I think just remind us how subjective smell is. even when the chemical source is probably the same.
Oh yeah, like Alexander Gerst.
ESA astronaut Alexander Gerst described it as, and I'm quoting here, a mixture between walnuts and the brake pads of my motorbike.
I mean, you have to wonder what his motorbike brake pads smell like to begin with.
That one definitely wins the award for most unique description.
No question.
Now, what's critical to establish here is the sensory contrast with the interior of the International Space Station.
Right.
Because while the vacuum-brought-in smell is exotic and strange, the ISS itself is far more mundane, yet, profoundly challenging to live in.
Well, the ISS is effectively a giant sealed canister, a tin can that gets reused indefinitely.
Scott Kelly famously compared the ISS smell to a room in a county jail.
Right. He said antiseptic mixed with garbage and just pervasive body odor.
Don Pettit had a different take. He described it as half machine shop, engine room, laboratory.
Which sounds about right.
Combined with the occasional fleeting waft of cooked food, maybe roast beef or something.
And the sources confirm this issue with microgravity, which is that because fluids and gases don't settle or disperse easily, any smell, whether it's cooking, antiseptic, or, the most unfortunate bodily ones.
Like farts.
Like farts, yes. They tend to linger far longer than they would here on Earth.
So while the vacuum smell is metallic and dramatic, the ISS interior sounds like a very long, cramped, and intensely industrial apartment.
Very smelly apartment.
To understand the origin of this metallic burnt steak aroma, we have to look at the two major chemical theories that try to explain it.
And this is where it gets really fascinating because it takes us from Earth orbit physics to deep space chemistry.
The first one, the ozone theory, is popular because a lot of astronauts, including Tim Peake, said the smell is like the clean, pungent, slightly metallic odor of static electricity.
Right, that smell right before a thunderstorm or from an old photocopier.
Exactly. Anyone who's been near an arsenic circuit knows that scent, and that is ozone, O3.
Ozone is a specific triatomic molecule of oxygen, and its formation is directly linked to high-energy interactions. And the mechanism they hypothesize here is, well, it's really elegant. Low Earth orbit, ILEO, where the ISS operates, has this very thin atmosphere.
But it's not a total vacuum.
No, not at all. And it's dominated by atomic oxygen, just single oxygen atoms. And that makes up about 90% of the material that's up there.
And that atomic oxygen, it must be highly reactive.
Incredibly reactive. And it just attaches itself directly to the exposed surfaces of the spacesuit and the tools during the spacewalk.
So it's just clinging to everything.
Exactly. So when the suit is brought back into the pressurized airlock, that hyperreactive atomic oxygen reacts with the cabin's normal breathable oxygen, which is O2.
And O plus O2 gives you O3.
Ozone. You get ozone. The process is highly exothermic. It releases energy, which is why it smells like high heat combustion or an electrical arc. It's the materials of the suit bringing the chemical components of the outer environment back inside to react with the inner environment.
Okay, so that accounts for the ozone, the gunpowder, the metallic side of the scent profile.
It does.
But that doesn't fully explain the descriptions of burnt steak or charred meat. That needs the second theory, and this one takes us much, much deeper into the cosmic void.
This second theory centers on something called polycyclic aromatic hydrocarbons.
Or PAHs.
PAHs.
Right, I remember you mentioned these molecules are found in things like soot and car exhaust here on Earth.
They are.
So are you saying we are smelling car exhaust in space? Why would these terrestrial byproducts be so common out there?
That's the crux of the theory. PAH are incredibly robust molecules. They're shaped kind of like chicken wire, and they're formed during inefficient combustion processes.
Okay, so on Earth, that's exhaust or burnt toast.
Right. But in space, they're key ingredients of soot, and they are generated when massive stars reach the end of their lives.
Here's where it gets really interesting. If we connect this to the bigger picture, when a massive star runs out of fuel, it doesn't just fade away.
No, it undergoes violent chemical processes. Sometimes it explodes in a supernova, and that's where all the heavier elements get made. Carbon, oxygen, gold, uranium, everything we see in the universe.
So this is the forge.
This is the cosmic forge. And the chemistry that happens in the star's outer shells during that death process is remarkably similar to the combustion of fossil fuels here on Earth. Stars that are relatively high in carbon compared to oxygen, they tend to form soot. And these PAHs are ejected out into space.
And they're stable enough to survive that journey, to just float around for eons.
They are. They're incredibly stable. And our noses, having evolved to detect danger signals like fire and smoke, are highly sensitive to these small PAHs.
So the question becomes, are the volatile remnants of cosmic combustion, the literal leftovers from some of the earliest stars, are they sticking to the surface of our spacecraft?
It creates this beautiful poetic link. Just like that million-ton cloud is held up by tiny density differences, these persistent, robust PAHs molecules born in stellar death are clinging to our ships, held up by their inherent chemical stability.
Which means when an astronaut reports a burnt steak smell, they might actually be smelling the volatile signatures of galactic history.
That's the theory. They're smelling the death of a star.
The scent profiles change drastically once we leave low Earth orbit and go somewhere like the Moon. This environment is less about atomic oxygen and much more about ancient, sterile dust.
Yeah, the Apollo astronauts who walked on the lunar surface, they brought back an odor that was consistently described by multiple crew members across different missions as smelling like spent gunpowder.
Charlie Duke, the Apollo 16 pilot, and Gene Cernan, the last man on the Moon, both reported this exact sharp smell.
Cernan was really specific about it. He remarked that once the dust was brought into the lunar module, it smelled like someone had just fired a carbine in here.
But chemically, moon dust lunar regolith, it's nothing like gunpowder.
Not even close. It's rich in silicon dioxide, glass, iron, calcium, magnesium. So the mystery persists. Why that smell?
Sounds like another contact reaction issue similar to the ozone situation on the ISS, but maybe more violent.
That's a good way to put it. The scent only occurs when that ancient airless dust encounters the warm, moist, oxygenated environment of the lunar module for the very first time.
Ah, so it's a first contact with air.
Exactly. The dust itself is incredibly fine and jagged. It's never been weathered or eroded. So the volatile molecules that have been absorbed onto the surface of those dust grains for billions of years get released. Or, and this is more likely, the highly reactive iron and silicon in the dust just rapidly oxidize when they meet oxygen for the first time.
And that causes that flash of a burning smell.
That's the idea. And what's critical is that the scent is fleeting. The dust doesn't smell like that once it's back on Earth, which means the reaction is swift and it's finite.
We can also estimate what deep space could smell like by using, sophisticated scanners and telescopes to analyze the chemical makeup of nebula and distant planets.
And these chemical profiles give us some truly bizarre conclusions about the cosmic deli, as you called it.
I think it fits.
It's fascinating because the building blocks for very familiar flavors are incredibly common out there in the universe. The nebula at the center of the Milky Way, Sagittarius B2,
Yes.
it contains huge concentrations of a chemical called ethyl formate.
And what's ethyl formate?
Yeah. Ethyl formate is the compound that gives raspberries their flavor, and because it's created from an acid in an alcohol reaction, it smells exactly like rum.
So you're telling me the core of our galaxy potentially smells like a colossal rum and raspberry cocktail.
Potentially, yes.
I'm starting to think deep space travel might be more appetizing than the ISS.
Well, you might not think that if you visited Jupiter's moon, Io.
Okay, what's wrong with Io?
Because of its intense, constant volcanic activity, scientists guess Io would smell of strong overtones of rotten eggs, a highly concentrated sulfur dioxide atmosphere.
Ah, not so appetizing.
And if you went into the dark interstellar clouds where new stars are forming, those icy compositions, water, alcohol, ammonia, carbon dioxide, they would combine to create a mix of ammonia and formaldehyde.
So giving the area a rather morgue-like accent.
Exactly. Not a great tourist destination.
This research isn't just for, sci-fi authors either. The sources indicate that NASA actually commissioned a perfumer
Stephen Pierce from Omega Ingredients.
to recreate these scents, specifically Ode to Space, the metallic burnt steak one, and Ode to Moon for the spent gunpowder.
And this serves a very practical purpose in astronaut training. It's about acclimatizing them to the sensory environment.
So no surprises.
Exactly. If a new smell is startling, it can break your concentration during a critical procedure. But it's also a powerful experiential education tool.
Imagine smelling the death of a star or the surface of the moon in a classroom setting.
That hands-on experience, they often do this one-for-one model. It's just a potent way to boost interest in STEM fields.
Absolutely. So the sense of smell, seemingly useless in a vacuum, becomes this critical piece of the human experience when we reintroduce pressure and oxygen. And understanding that reaction, that chemical and physiological transition between environments, it leads us perfectly into our next section, how we use artificial environments to test perception.
Yeah, this is a fascinating turn.
The physiological challenges of space are constantly monitored, but astronauts also report a persistent, less dramatic issue, which is a decline in flavor perception. Space food just doesn't taste as good.
And this decline is often cited as a major issue for morale on long-duration missions. I mean, food is comfort.
Of course.
Initially, this was largely attributed to the fluid shifts caused by microgravity. With fluids pooling in your upper body, you get this kind of perpetual head cold or congestion that dulls your sense of smell.
And smell is fundamental for flavor perception.
It's almost everything.
But the adaptation process is pretty quick, right? Astronauts generally stop feeling acutely congested after a few weeks. So what else is at play if the flavor dullness persists?
It could very well be the psychological effects of the environment itself. Astronauts are living in these highly controlled, confined environments like the ISS, which has very low sensory stimulation compared to Earth.
Right. It's sterile, it's monotonous.
And research from extreme analogs, submarines, Antarctic stations, deep sea habitats, suggests that people in these controlled, low stimulation environments can experience a measurably reduced ability to smell and taste over time.
So the question is that a physical change or is it psychological adaptation?
That remains a critical area of research.
Yeah.
And since we can't exactly run large, long-term sensory tests on orbit with hundreds of participants,
We need ground-based analogs, things that can accurately mimic the isolated, confined, and often stressful environment of a spacecraft.
and that's where technology steps in. The research detailed in your sources use virtual reality.
Oh, okay.
They created a high-fidelity VR simulation of the cluttered, confined, and noisy atmosphere of the ISS. VR offers what they call high ecological validity.
Meaning it feels real.
It feels real enough to trick the brain into thinking it's somewhere else. And that is critical when you're testing context-sensitive processes like odor perception.
So the methodology in this study was brilliantly targeted. Participants were exposed to 3 common food odors: vanilla, almond, and lemon.
Right, very distinct smells.
And they rated their intensity in 2 different settings: a simple, quiet, neutral lab context, and then a full VR simulation of the ISS space laboratory.
Complete with virtual floating objects, constant clutter, distracting operational background noise. The whole package.
The first step was validation. Did the VR actually work?
And it did. The simulation successfully evoked low to moderate feelings of loneliness and confinement among the participants. It confirmed that the simulated environment was effective at creating that psychological context of isolation.
But the results on the odors themselves were the shock.
They really were.
Wait a minute. Because I would have expected the exact opposite, based on the congestion theory. If astronauts are feeling congested and confined, you'd think the odors would be dulled.
That's the logical assumption.
But the data says vanilla and almond odors were perceived as significantly more intense in the VR space context compared to the neutral context. Why would the brain boost perception under conditions of stress or confinement?
That is the central cognitive paradox this research uncovered. It indicates that context doesn't just dull all senses, and it doesn't affect all chemical profiles equally. It suggests the brain might be trying to compensate for low stimulation.
That's fascinating. So the researchers immediately had to look at the chemistry to find this specific connection. What did vanilla and almond have in common?
Exactly. They used gas chromatography, mass spectrometry analysis, GCMS, to link the vanilla and almond results, and they found that both samples contained high concentrations of a compound called benzaldehyde,
Benzaldehyde.
which is known for its distinct almond-like sweetness and aroma. It's the key chemical in both.
And the lemon odor, which is dominated by completely different compounds like limon.
Right, typical citrus terpenes.
That wasn't contextually affected at all. Its intensity didn't change.
Which strongly suggests that specific chemical profiles, namely sweet, highly aromatic ones like benzaldehyde, might be inherently more sensitive to the psychological stress and confinement of the simulated spacecraft than other, perhaps more robust chemical profiles like citrus.
So the sweet smells were amplified simply because the brain was placed in a confined context.
That's what the data points to.
That in itself is a huge finding. But here's where it gets really intricate: the role of individual variation. The researchers didn't see uniform amplification across everyone.
No, they didn't. They clustered the participants based on their baseline sensitivity to these odors in the neutral setting. And they found that the group categorized as having low sensitivity to the almond odor in the neutral setting.
The ones who could barely smell it to begin with.
Those were the ones who experienced the most significant increase in intensity when they were immersed in the VR context.
So the environment didn't just boost the scent perception universally. It specifically amplified the perception for those who are otherwise biologically less sensitive to that smell. That's profound.
It is. It means psychological context, like confinement and loneliness, can fundamentally override or compensate for lower biological input. It changes how the brain processes chemical information.
It absolutely proves that our sensory experience is not a passive reception of data. It's an active, context-dependent construction by the brain.
Which raises crucial questions for deep space travel. If we know that certain sweet, volatile compounds are amplified by the confined, isolated context, we can anticipate how this might affect the palatability of space food.
And you have to be careful. Higher intensity does not equal higher liking.
Not at all. An amplified sweet or almond smell could easily become overwhelming or even nauseating on a long flight to Mars.
It seems the body's attempt to thrive, or at least cope, in a challenging environment extends even to how the brain processes scent. It could alter the entire eating experience for future Mars travelers. This makes the adaptation phase for astronauts not just a physical adjustment, but a deep psychological and sensory one.
And that leads perfectly into the wider physical effects.
Moving from the fascinating complexities of odor perception, let's look at the macro-human body. The sheer number of bizarre adaptations, injuries, and health threats astronauts face in orbit is, it's just astounding. We need to understand the toll that living outside of gravity's protection really takes.
The immediate and perhaps most benign adaptation is height change.
Right, they get taller.
They do. Astronauts can temporarily grow up to 3% taller, potentially gaining up to 2 inches, because the vertebrae of the spine expand without the constant compressive force of gravity.
It's a fun fact, but I imagine it's not actually fun.
No, it can lead to back pain and nerve issues. And yes, they do return to their original height after a few months back on Earth.
And then you have the fluid shifts, which dramatically affect their appearance.
The puffy face, yeah.
On Earth, gravity pulls our fluids down toward our feet. In orbit, that fluid redistributes evenly throughout the upper body.
Which causes the puffy faces, the bloodshot eyes, and these relatively skinny bird legs in the first few weeks, until the body adjusts its overall fluid balance.
But the short-term aesthetics are one thing. The long-term issues are far more serious. They center on rapid degeneration.
The body is smart. It quickly recognizes that it doesn't need to support itself against gravity. So it starts getting rid of what it doesn't need.
Which leads to rapid muscle atrophy and severe bone density loss.
Up to 1 to 2% per month?
Per month. To put that into perspective, an average elderly postmenopausal woman loses bone density at maybe 0.5% a year.
So astronauts are losing density at a rate that's 20 to 40 times faster.
That's terrifying.
It is. And this is why 2 hours of strenuous, specific daily exercise using specialized resistance equipment is absolutely mandatory, just to maintain a healthy baseline for return. They are constantly fighting the fundamental physics of their new environment.
And it gets worse. There's a premature aging effect.
Extended microgravity seems to stress the body in these unique ways. Astronauts exhibit drier, thinner skin, and critically, a stiffening of their arteries.
What does that mean, a stiffening of the arteries?
It means their cardiovascular system begins to resemble that of someone 20 to 30 years older. It dramatically increases their risk of heart problems and stroke upon return to Earth.
Now let's discuss some of the truly unwanted surprises of life in orbit. Space sickness.
Space adaptation syndrome. It affects more than half of all astronauts in the first few days. Intense nausea, headaches, vomiting, it's miserable.
The sources mention that the severity of these symptoms is informally measured in Garns.
Yes, after astronaut Jake Garn.
He suffered so severely during his flight that his experience became the standard unit of measurement for space nausea. That's one of the worst legacies you can leave behind.
It certainly is. But perhaps the most visceral and, frankly, gruesome physical adaptation involved their hands.
Okay.
The bulky, pressurized gloves they have to wear for spacewalks often cut off circulation and create high pressure points on the fingertips.
I can imagine.
And this pressure can cause the nail bed to separate from the digit. The condition is called fingernail delamination.
Oh, wow. I have to pause on that. The sources confirmed that this is such a consistent and agonizing risk that some astronauts actually preemptively remove their own nails before certain missions.
They do. To avoid the pain and the agony later on, it just speaks to the extreme physical sacrifice required to perform basic maintenance outside the craft.
It highlights the brutal reality of working in a pressurized suit against a vacuum. And the sensory impacts don't stop there. Vision changes are also extremely common.
Nearly half of astronauts on longer flights experience blurred vision.
Why?
because the fluid pressure affects the optic nerve, causing the eyeballs to flatten slightly and the retinas to change. In some cases, the deterioration can take years to return to normal, if it ever fully does.
And then there's the cosmic weirdness that happens when they try to sleep. Astronauts consistently report seeing flashes of light.
Like fireworks or streaks, even with their eyes closed?
That isn't a malfunction or a dream?
No. That is caused by high-energy galactic cosmic rays particles traveling near the speed of light shooting right through their skulls and interacting directly with their visual cortex or the retina in the eye.
It's a constant, low-level radiation bombardment that gives them a visible, albeit temporary, light show.
A very unsettling one.
And finally, the subtle psychological toll. Post-flight coordination.
A subtle but pervasive consequence of adaptation. Astronauts return and frequently report dropping everyday objects, cups, pens, keys.
Because they momentarily forget that gravity is a thing again.
Exactly. After months in weightlessness, it takes a significant period for the brain to stop anticipating it and fully re-engage the necessary effort for terrestrial life.
If the side effects haven't scared you off, let's consider the odds of even getting there. Becoming a NASA astronaut is statistically nearly impossible.
The statistics are astronomical, literally. In a recent selection round, for example, NASA got over 18,300 applications.
And how many did they pick?
They selected 12 people. That's an acceptance rate of just 0.065%. It is far, far harder to become a NASA astronaut than it is to get into Harvard or Yale.
That puts the intensity of the ambition into perspective. So persistence naturally becomes key.
Oh, absolutely. The sources mention one particularly determined individual, Clay Anderson, who applied 15 times before he was finally selected.
15 times. That's nearly 2 decades of effort for a single chance.
And the training demands reflect this intense selection process. Candidates already have a profound background in science or engineering, but the training adds these mandatory skills, like learning technical Russian.
Still necessary for ISS operations, particularly emergency procedures.
And surviving rigorous physical tests.
Like the extreme water survival test, swimming 3 lengths of a 25-meter pool while wearing a full flight suit and heavy tennis shoes.
It's designed to simulate bailing out of a spacecraft over water. It requires massive core strength and mental fortitude.
And they also use some surprisingly low-tech simulation methods for weightlessness.
The giant air hockey tables, I love this detail.
It's brilliant.
It's a beautifully simple, analogous system. They practice maneuvering massive multi-ton objects in weightlessness using these giant air hockey tables. They affix air cushion pads to the large mock-up objects, turning the floor into a massive, low-friction surface.
So they can practice complex tasks like operating manned maneuvering units and achieving precision movement without gravity getting in the way.
The preparation for life in space is exhaustive, but the planning for death in space is, well, it's rather limited.
Primarily because of international concerns over environmental contamination. The UN prohibits space littering.
And that includes bodies or biological waste because of the risk of collision with operational satellites or contamination of other planets.
So simply releasing a body into space, as tempting as that cinematic option might be, is forbidden.
Absolutely forbidden, yet storing a corpse inside a pressurized spacecraft for months or years on a long-duration mission is highly problematic, both ethically and logistically.
So NASA, recognizing this grim reality, collaborated with a burial company on a rather chilling concept called body bag.
The concept involves sealing a deceased astronaut in a specialized, airtight bag. That bag is then attached to the exterior of the spacecraft.
So it's outside.
Exposed to the extreme cold of space, the body freezes solid. And then, due to the micro vibrations and intense thermal cycles of space travel, the frozen body gradually vibrates and shatters into fine dust particles during the journey.
A frosty funeral.
That's what they called it. The idea was to return the materials, not the body, to Earth for disposition.
It transitions from extreme physical risk and training to the most extreme end-of-life scenario possible. The physical and logistical demands of living outside our gravity are just relentless.
Relentless.
We started this deep dive with the counterintuitive fact of a million-ton cloud floating gently above us. And we have to transition now to the most profound realization of all. The material we are made of.
Yeah.
The ultimate cosmic density.
To understand our origin, we have to go back to the Big Bang. The universe's first elements were formed in its aftermath.
Specifically hydrogen atoms, the simplest element.
Right. After about 3 seconds of cooling, Hydrogen is the primordial element. It's the Big Bang dust.
But the universe needed bulkier ingredients than just hydrogen to create planets and people.
Mhm.
And that's where stars come in. They act as cosmic furnaces.
Stars fuse hydrogen into helium, and then they continue this fusion process, creating heavier and heavier elements all the way up to element 26, which is iron. This entire high-pressure, high-temperature synthesis process defines stardust.
So astrophysicists confirm that almost every element on the periodic table beyond hydrogen is essentially stardust.
Forged in the hearts of distant, massive stars.
Which leads us to a fascinating calculation about our own composition. The human body is composed of roughly 7 times 10 to the power of 27 atoms.
An unimaginable number.
And when we break that down, approximately 40% of those atoms are hydrogen, Big Bang dust.
So far, so good? 40% Big Bang, 60% stardust atoms. But here's the profound shift in perspective. Because stardust elements like carbon, oxygen, nitrogen, iron, they're so much heavier than hydrogen.
So the mass calculation changes dramatically.
It changes everything.
Because these heavier elements form our bones, our organs, all the carbon structures, they account for almost all of our weight.
Over 93% of the mass in your body is stardust. The vast majority of your physical being, your bones, your blood, the carbon in your DNA, is the volatile, heavier leftovers of dying stars.
When you look in the mirror, you are looking at the molecular remnants of supernova explosions that occurred billions of years ago.
It truly gives weight to that poetic phrase, "We are all made of stardust." It's literally true.
And these building blocks weren't just created, they were delivered right here to the early Earth by cosmic messengers.
Meteorites, ancient, pristine pieces of celestial bodies. They are the key.
What did they bring?
They delivered critical organic compounds, like amino acids and carboxylic acids, which are the precursors for proteins. But more importantly, they delivered reduced phosphorus to early Earth.
Okay, let's clarify that distinction. Why is reduced phosphorus so important? What state was phosphorus in on early Earth?
That's a crucial chemical detail. On early Earth, phosphorus existed primarily in highly oxidized states. It was typically locked up in inert, non-reactive minerals called phosphates.
So it was there, but it wasn't usable.
Exactly. These oxidized forms are very difficult to use to build complex molecular structures. The reduced phosphorus delivered by meteorites, however, was in a much more chemically reactive form.
And that reactive reduced phosphorus was essential because its oxidation to phosphates provided the key chemical mechanism, the energetic backbone for the generation of DNA and RNA.
Without those meteorite deliveries, life as we know it, built on those fundamental precursors, would have struggled immensely to get off the ground. Meteorites aren't just space rocks, they are the fundamental delivery mechanism for the ingredients of our biology.
Speaking of space rocks, we need to talk about Jupiter. If meteorites are the delivery trucks, Jupiter is the solar system's colossal gravitational bouncer.
And protector. It's immense. Jupiter is 2.5 times more massive than all the other planets in our solar system combined.
And that's just hard to even imagine.
Its sheer scale just dominates the gravitational dynamics of our whole solar neighborhood.
And its size is only matched by its incredible rotational speed. It spins the fastest of any planet, a full rotation in just 10 hours.
And this rapid spin causes it to noticeably flatten at the poles and bulge at the equator, a 4,600-kilometer difference between its polar and equatorial radii.
And all that mass translates to intense gravity.
2.5 times Earth's gravity. And this force gives Jupiter its incredible cosmic power to influence distant objects.
And that power was demonstrated dramatically in 1994 with the collision of comet Shoemaker-Levy 9.
Jupiter's gravitational pull was so intense as the comet passed that it literally tore the comet apart.
Wow.
It created this highly visible, mesmerizing string of pearls of fragments.
And then over the course of several days, it just pulled those fragments directly into the planet's atmosphere, one after the other.
It was a landmark event. It was the first time we, as humans, had direct, real-time observation of two extraterrestrial solar system bodies colliding.
And for astronomers, this was like the Super Bowl.
It was. And that collision was highly useful for chemical analysis. It allowed astronomers to observe and analyze new chemical components in the Jovian atmosphere that hadn't been seen before.
Like what?
Things like diatomic sulfur and carbon disulfide. It gave us a unique spectroscopic window into the planet's composition.
So Jupiter acts as the gravitational shield of the inner solar system, just tidally manipulating and cleaning up debris that might otherwise pose a threat to us.
That's the theory.
And while we observe these intense, powerful events, The planet's most famous feature, the Great Red Spot, just continues its centuries-long existence.
It's the definition of a persistent atmospheric phenomenon. It's a massive anticyclonic storm,
Big enough to hold 2 or 3 Earths.
comfortably inside its boundary, and it's been observed consistently for at least 350 years.
But it is shrinking.
It is. Observational data confirms that while it is persistent, it is currently shrinking, suggesting that even this gargantuan storm is subject to planetary dynamics over geological timescales.
We've talked about cosmic origins and planetary protectors, but what about the rocks that get close enough to visit Earth? We need to quickly clarify the terminology.
Right. Meteoroid, meteor, meteorite. It's a constant source of confusion.
Right, it's simple.
It is. It's just context dependent. A meteoroid is the object while it's still in space.
When it enters the atmosphere and creates that visible streak of light, what people call a shooting star, it becomes a meteor.
A particularly bright meteor, one that shines brighter than the planet Venus, that's called a fireball.
And if it survives the fiery trip and actually lands on the ground, then it's a meteorite.
Simple as that.
And we can deduce some things about the chemical composition of that meteoroid simply by watching the color of the light trail it leaves behind.
Yeah, the dominant composition colors are signature emissions when the elements vaporize. It's spectral analysis in motion.
So sodium burns a visible yellow.
Nickel shows up as a distinct green, and magnesium emits a brilliant blue-white trail. These colors help scientists determine the rock's original type.
And for a meteoroid to actually survive that atmospheric entry and become a meteorite, it needs to be incredibly sturdy.
Generally of asteroidal origin, not cometary, and bright enough magnitude, -8 to -10, to retain visible light below 20 kilometers altitude.
And below that point, the intense burning away of material, the ablation, it stops.
It stops, and the surviving pieces enter the final dark flight stage. They fall the rest of the way at a terminal velocity of 200 to 400 miles per hour, essentially as inert, cold rocks that hit the ground minutes later.
And finally, the sounds. We know the massive ones generate a sonic boom, but because sound travels slowly, that comes several minutes after you see it.
But witnesses also report simultaneous sounds, sizzling, popping, or crackling, right as the fireball passes overhead.
These are known as electrophonic sounds.
Their origin is still a bit elusive scientifically, but the leading theory is fascinating. The fireball, due to its rapid motion and ionization, emits intense, very low-frequency radio waves, VLF waves.
And these waves travel at the speed of light. They reach you instantly.
Exactly. And these VLF radio waves, despite being silent themselves, they interact with common objects, nearby metal fence posts, power lines, or even your own hair and eyeglasses.
And that creates a localized, instantaneous vibration that you perceive as sizzling or cracking, matching the visual spectacle.
It's the final, peculiar flourish of a cosmic visitor, a silent fireball, followed by an instantaneous popping sound triggered by invisible radio waves, and then, minutes later, a thunderous sonic boom generated by the shock wave that arrived at the speed of sound.
So we have covered so much ground today, from the bizarre chemistry of stellar death that makes our airlocks smell like burnt steak, to the extreme physical adaptation of the human body in microgravity.
Including the unsettling reality of preemptive fingernail removal.
And we learned the profound truth that over 93% of our physical mass is ancient stardust, delivered by cosmic messengers in the form of reactive reduced phosphorus.
But perhaps the greatest insight for me relates to our own sentience.
We saw that our sensory perceptions are deeply conditional. They're not absolute. The intensity of a simple almond smell can be fundamentally altered, even amplified, simply by tricking the brain into believing it's confined and isolated in a cluttered space environment.
So what does this all mean?
It means that as we push toward sustained life on Mars or in the distant asteroid belt, the engineering challenge isn't just shielding the body from cosmic rays or preventing bone decay. It's about maintaining the mental and sensory well-being of the crew.
Absolutely. The VR study demonstrated that the brain will actively try to compensate for the isolation and low sensory input of confinement. It specifically boosts the perception of certain chemical profiles, like the sweet notes of benzaldehyde for those who are otherwise less sensitive.
If a psychological analog can amplify a sensory experience for the less sensitive, we've gained a massive, actionable insight into human resilience.
The final provocative thought is this. We now know that context and environment fundamentally alter perception. So how can we leverage immersive technologies, customized architecture, and custom flavor chemistry, knowing which chemical profiles are sensitive to context to custom tailor future habitats and food systems?
Right. We need to move beyond just designing food to prevent malnutrition.
To engineering an environment where astronauts thrive psychologically, where the food isn't just palatable, but is actively enjoyable, potentially using the environment itself to boost their lagging senses. That is the next great frontier of long-duration space exploration.
It means there is always more to learn and more to discover, both in the cosmos and inside ourselves. Thanks for joining us for the deep dive.